So we're starting off looking at the first one here. It says giga. The abbreviation is a capital G. And scientific notation is 10 to the ninth. We want to think about what 10 to the ninth means. All right, 10 to the ninth means a 1 with 9 zeros after it. All right, what's a 1 with 9 zeros after it? What number is that? What's that?
1 billion.
That's a billion. You got it. So it turns out giga means a billion. So there are 1 billion. Sorry, I keep hitting the wrong button here. There we go. There are 1 billion grams in a gigagram. All right, so giga is our biggest prefix of all. So we're starting up on top with the really big prefixes. I'm going to put that in the margin over here. I'm going to write, this is the side with the big prefixes. We're going to work our way down to the very small prefixes down there at nano. We're just going to work our way one at a time. Next, we've got mega. So mega, its abbreviation is a capital M. So notice that's capital. That's important there. 10 to the sixth is the scientific notation, and we would say there are 1 million. So now we've just got 6 zeros because it's 10 to the sixth. There are 1 million grams in a megagram. You might have heard there's like a lottery game called Mega Millions. So that helps me remember that mega means a million there. There's 1 million grams in a megagram because mega means a million. All right, now we're getting to more familiar ones like kilo. You would probably have already heard of kilo quite a bit. Kilo is a lowercase, k is the abbreviation. It's 10 to the third. All right, so what number would 10 to the third be? 1,000, you got it. So we just take it 3 zeros at a time there. There's 1,000 grams in a kilogram. Next up, I've got this one base here that people are always like, why do you put base there? You don't have to fill anything in. But this is the line between the big prefixes and the small prefixes. Everything below this gets into things that are very small, smaller than a gram. First, we're going to study centi. Now, there are more prefixes than just these. So you may have learned some prefixes before, and they talked about deci and deca. Those are also real prefixes, but we don't use those as much in a chemistry class, so I just left those out. Next, we've got centi, though. So centi means 10 to the negative 2. But look at this. So things start to change a little bit here. Now, instead of saying there are 100 grams in a centigram, I'm now saying there are 100 centigrams in a gram. So after we went under that gray line, the order switches because we're dealing with lots of little parts inside of the whole. All right, then we get to milli. Milli says 10 to the negative third. There are 1,000 little milligrams in a gram. So a milligram might be like a grain of salt, or a few grains of salt would be a milligram. We're on a really, really small mass now. All right, our next one is micro, and you'll notice the symbol for micro, it almost looks like a U. This symbol that we see for micro, that is called it's a Greek M. It's called a mu. And, you know, we've got a lot of things that start with M. We've got mega, we've got milli, and now we've got micro. Well, they ran out of M's with capital and lowercase, so they had to go to the Greek alphabet. Just like with coronavirus, they have to name all these things with the Greek alphabet. So one day there will probably be a mu variant of the coronavirus because we get all these Greek letters for the variants. But we've got the micro is mu, and that means 1 millionth. So that means there's 1 million little micrograms in a gram. All right, and then finally we're at 10 to the negative ninth. So Henry, why don't you take a picture of this or something because we'll be moving on from it in a second. Okay. Here we've got 1 billion little nanograms in a gram. You may have heard of like a nanosecond before. So there's 1 billion nanoseconds in a second. There's 1 billion nanograms in a gram. So just for examples, I've used grams as my base unit throughout this. We said gigograms and grams, But you can do with these prefixes all the same things we did with grams. You can do all these same things with seconds. You can do it with meters. So just like I said, there are 1 billion nanograms in a gram. I could say there's 1 billion nanometers in a meter, or 1 billion nanoseconds in a second. You can apply these prefixes to any of the SI units: amperes, meters, grams and kilograms, seconds, and all of those. All right, does anybody need more time with this chart? So this is the chart we're going to use to do our next chart that's on your sheet there. And this next chart is very similar to what you'll do on the homework, so make sure you understand how to do this kind of a chart. So the first one was done for us, and we're practicing with this. It said the unit is nanoseconds, and I know that because when you look at the units that's shown here, the very first one, that's going to be your prefix letter. So you would use that prefix chart to figure out that that meant nano. All right, and then the second letter is going to be whatever the base unit is. In this case, it's S, and that's where the seconds comes from. So in that way, that's why we call it N for nano, S for seconds. So it's kind of like translating the symbols. The first one is a prefix, the second one is the base unit. The prefix meaning, I just went straight to that chart and I found it. So this box I just get straight from the chart above that you just filled out. All right, and then I have to do the sentence. Well, if I look up at my chart, after nano, my chart says there's 1 billion nanograms in a gram. Sometimes people will write that for this, but I'm like, no, this one's not about grams, this is about seconds. So you just swap out the word grams for seconds. So there's 1 billion nanoseconds in a second. So I'm going to put this kind of in parentheses here. This is kind of where you're plugging in. Instead of grams, you plug in specifically what your question is about for your base unit. Now the next one is about something grams. So let's just look at it. So if it says kg in the box, all right, what should I probably put? Yeah, I'm going to put kilograms there. Good. All right, they did the second box for me there. Then I'm going to need to put my scientific notation meaning. So go up to your chart. What's the scientific notation meaning for kilo on the first chart that we made? Dalton? What's the scientific notation meaning for kilo? You got it. So he went up to that chart, he found kilo, and then he found that it means 10 to the third, which is 1,000. Now, because this one is about grams, we can basically rewrite the same sentence that comes next. So I'm going to say there are blank grams or kilograms in one blank. So Ian, what would I write for my sentence on this box here?
For the kilograms?
Yeah.
There are 1,000 grams in 1 kilogram.
You got it. All right. Now the next one, you may or may not know what the L part stands for. I'm going to go, what do you think the L stands for? Yeah, liter. So in this case, I'll go ahead and tell you that's liter. L is going to be for liter. But yeah, let me get, Ethan, what's this? What are we going to put in the first box then for this one for ml? Yeah, milliliter. Good job. I like to capitalize the L. Sometimes you see it capitalized, sometimes you don't. All right. The next box, scientific notation box. Tanner, what goes in the scientific notation box here? Good job. Milli means 10 to the negative third. Now for our sentence part. Don't use the word gram here. Always substitute it with the word liter. So if you look for milli on your chart, it's going to tell you about it in grams, but you'll just kind of substitute out the word liter. So Tyler, what would I put for my sentence here? Good job. 1,000 milliliters in 1 liter. What if somebody said there are 1,000 liters in 1 milliliter? That would be wrong, exactly, because a liter is pretty big, a milliliter is really small. So the order is important, huh? All right, now we've got CG next. Braylon, what do you think CG might stand for? All right, yeah, so the C, we know the C, if we look at our chart, C stands for centi. And then, well, the second one isn't going to be a prefix. The second one is always going to be your base unit. So gig is a prefix. What base unit starts with a G that we're using here? Gram, yeah, so it's centigram. So I'm actually glad you mentioned that. It's always, if there's 2 letters, the first one is a prefix, the second letter is a base unit. If you ever have just 1 letter, it's got to be the base unit. But if you have 2 letters, the first one's a prefix, the second one's a base unit. Now let's do some scientific notation here. Jordan, what's the scientific notation meaning of centi?
10 to the negative 2.
You got it. 10 to the negative 2 means 100th. All right, so Brady, what would our sentence be here? You got it, yeah. There are 100 centigrams. Just like there's 100 cents in a dollar, so you can see where that word centi came from. There's 100 centigrams in 1 gram. So centigrams are small amounts. All right, next we got this weird symbol here. All right, what prefix does that weird symbol mean? And so what are we going to put in the first box for this one? Jade? Micro. And then G stands for grams, yeah. So you can imagine a microgram must be a really small amount. Like a little tiny droplet of water would be a microgram. Teeny tiny droplet of water. Okay, Isabella, what's the scientific notation meaning for micro? Good job. Now for our sentence. Brandon, what would I write for my sentence here? You got it. So this one comes straight from the chart because it's about grams. So again, there's something very similar to that you'll do on your homework assignments. I wanted us to do several of those. The most common mistake I think people make is they don't know how easy it is to swap out the word liter for grams. So like in the red one in the middle, I didn't say there are 1,000 milligrams in 1 gram. I said there are 1,000 milliliters in 1 liter because in this case our base unit we're basing everything on is the liter. All right, the other thing we're going to practice with today is the temperature units. And with temperature units, we're going to learn about converting between Celsius and Kelvin. So back on your notes page with your notebook paper, we're going to just pick up with some stuff on Kelvin and Celsius temperatures. The 3 major temperature scales, we all know about Fahrenheit. That's what we use in the U.S. For whatever reason, the rest of the world uses Celsius while we use Fahrenheit. Celsius is a really nice unit for chemistry because it's based on water freezing at 0, water boiling at 100 degrees. So it's a nice, even kind of a scale, 0 to 100. With Fahrenheit, the units aren't, the numbers just aren't quite so friendly to work with. In chemistry, we're going to use a lot of Celsius and Kelvin. They say the Fahrenheit scale is based on you as a human, how you feel in a way. So if it's 0 Fahrenheit, you're really cold. If it's 100 Fahrenheit, you're really hot, like a really, really hot day in the summer. Fahrenheit's really good for weather and for how you feel. Celsius is more about water. If it's 0 degrees Celsius, then water is freezing. If it's 100 degrees Celsius, water is boiling. But a really, really hot day would be like 38 or 39 degrees Celsius. So on the Celsius scale, if you're up near 100 Celsius, you're dying because you're about to start boiling, actually boiling. So on the Celsius scale, a hot day, like maybe a really hot day in a tropical country might be 40 degrees Celsius, maybe a little bit more than that, but not much more than that. All right, and then the Kelvin system, Kelvin is based on matter and vibrations of matter in the particle level. The atom actually stops moving. Does anybody need more time here? Okay. All right, so if we want to compare these for Fahrenheit, think about freezing. So the freezing point of water and the boiling point of water is what I want us to compare on these guys. Raise your hand if you know the freezing point of water on the Fahrenheit scale. 32. Ian knew it too. Thanks, Ian. 32. So a lot of us know that because we're interested in the freezing point on Fahrenheit for snow days and things. What about the boiling point? What's the boiling point on the Fahrenheit scale? Ian?
212 degrees Fahrenheit.
Thank you, 212. Those weird numbers, aren't they? All right, what about Celsius? What is the freezing point on the Celsius scale? 0 degrees Celsius. So let's put a star by this. If you learn one thing in this class, I'd like you to walk out of here knowing the freezing point and boiling point on the Celsius scale. 0 degrees Celsius. What's the boiling point on the Celsius scale? Who knows that? 100, you got it. So there we go. That's why the Celsius scale is so nice and simple. It's just 0 and 100. You don't have to. You can imagine if you were from a different country and you moved to the U.S. and you're like, why do you do everything with 32 and 212? Those are weird numbers when they're used to 0 to 100 in other countries. All right, and then last, Kelvin. Now Kelvin is really kind of the far out one here. Kelvin is offset from the Celsius scale by exactly 273. You see, Kelvin can never go negative, so Kelvin 0 is really, really, really cold. And then Kelvin's boiling point is 373. So notice with Kelvin, we don't use a little degree sign, we just put a capital K for Kelvin. And also how, even though the Celsius and Kelvin temperatures are very different, when they change by 100 degrees, the other one changes by 100 degrees. So each little difference is the same, they just start and end in different places. All right, so the Kelvin scale is kind of maybe a newer one to learn about. It's based on absolute zero. Absolute zero is the coldest possible temperature in the universe. So if you're out in deep middle of space without being close to any star or any source of heat, you might be very close to absolute zero. It's the temperature at which there's no kinetic energy. That means the particles aren't even moving at all. When you learn about states of matter, you learn about solid, liquid, and gas, maybe plasma. Turns out there's another exotic state of matter, which would be an absolute zero. It's called the Bose-Einstein condensate, the coldest possible temperature. So the idea is if you have a gas, the particles are moving around, flying around, bouncing off of each other, and you cool it down enough until it becomes a liquid, the particles have to start sliding beside each other, they're not moving as fast. And then they become a solid and they're just vibrating in place, they don't have a whole lot of kinetic energy. But if they slowed down and got really, really cold, you could pull all the kinetic energy out of them and they would stop moving at all. Is it possible to move any slower than not moving at all? That's why absolute zero, we call it, is the coldest possible temperature, and you can't have negative temperatures on the Kelvin scale because the particles can't go any slower than not moving at all. And temperature is really just measuring the motion of the particles. So if they're standing still, they have zero temperature on the Kelvin scale. And when that happens, the state of matter changes from a solid to something really exotic where it loses all of its properties. It's more of a theoretical kind of state of matter, and it's called the Bose-Einstein condensate. I think this is the last one I'm going to make you right here. Celsius to Kelvin conversions. To go from Celsius to Kelvin, you just add 273. So I say K equals C plus 273. If you ever do the operation and you get a negative Kelvin temperature, you know you did something wrong because it's impossible to have a negative Kelvin temperature. And that's the last thing you have to write in your notes. I'm going to pass out the assignment and we're going to start it together now. You get that down because first thing you'll do is some of that conversion stuff. The first page is about Celsius and Kelvin conversions, the stuff we just talked about. Then on the back of this, there's a chart that you're going to fill out that's a lot like the chart that we just did together a minute ago, where you've got the prefixes. 13 and 14, the bottom here, just with those for now. We're going to do those together probably on Monday. So you just need to do the front of this and the chart on the back. And we're going to start the front of it together there, doing some of those conversions. There you go, Ian. Take one and pass it back, please. Take one and pass it back, please. You're welcome. I'm going to run some calculators too. For these conversions, you can do it without a calculator for sure. If you like to do math without a calculator, feel free to. But if you're like me, sometimes have a calculator. You gave us that. Oh, thank you. Just grab a calculator and run around if you don't have your own. 5, and 6. See these together. Calculator here? Sure. Calculator working? Okay. So the first three I'll have you kind of answer based on some of the stuff we talked about. But let's drop down to number 4 on the front page. And it says to convert this to Kelvin. So it says 0 degrees Celsius. We have to put this answer in. All right, well, it's easy. We remember K equals C plus 273. So your Kelvin temperature, you don't need a calculator for that, do you? It's just 0 plus 273. And then we'll put the unit on there too. So for my answer, I'll say 273. And then the unit is just Kelvin, K for Kelvin. Let's try number 5. It says negative 50. That's a really cold temperature, too cold to be out in. So negative 50 degrees Celsius. All right, we're just going to say K equals negative 50 plus 273. What's that going to be? 223 Kelvin. Again, if you ever get a negative Kelvin temperature, you did something wrong. You can have negative Celsius, but you can't have negative Kelvin. All right, so on that 4 through 7, you just take what's given, you add 273, boom, it's in Kelvin. What if we're going the other way, like on number 8? It gives us Kelvin, and we're going to turn it into Celsius. How would we go the other way from Kelvin into Celsius? Yeah, good. You're just going to subtract instead. So on this one, we're going to take whatever's given, and I'll take that off of the math part, and we'll subtract 273. What's 100 minus 273? Can I have a negative Celsius temperature? Yep, I sure can. I just can't have a negative Kelvin. So I better put Celsius here. The unit here is degrees Celsius then. We'll usually do this, the converting from Celsius to Kelvin, but occasionally we might go the other way. All right, so for the remainder of class, just continue working on those. Try 1, 2, and 3. If you have a question on 1, 2, or 3, just do your best to answer those. And then you may also want to get started on the back on that chart. It's very similar to the chart that we filled out together as some practice questions on there, so you can kind of use that one as an example.